Everything you need to stay alive is being supplied to you right now by a planet you did not build and cannot replace. The air is moving through your lungs because something very old and very large decided to grow trees. The water reached you through a recycling system that has been running for 4 billion years without a single interruption. You are warm because a magnetic field you cannot see is deflecting radiation that would otherwise strip you to the bone. None of this required your permission. None of it sent you a bill. Earth simply runs, and you run with it. Now imagine leaving, not for a weekend, not for 6 months on a space station stocked with supplies launched from the ground. Imagine leaving the way a ship leaves port, self-contained, carrying everything it needs, not expecting to resupply. The Apollo astronauts made it to the moon and back on stored oxygen, stored water and food sealed in pouches. That worked for 2 weeks. It would not work for 2 years. It would not work for 20. A mission that lasts long enough to reach another star, or even to build a permanent presence somewhere beyond Earth, cannot run on what it brings. It has to run on what it makes. That is the question at the center of this video. Can a spacecraft feed itself, recycle its own air, grow its own food, and generate the gravity its crew needs to stay healthy? Not for a mission, but indefinitely, the way a planet does? Can we take everything Earth does silently and automatically, and rebuild it deliberately, inside a metal structure moving through the dark? If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. The engineering required to answer yes is staggering. Artificial gravity from rotation, closed-loop life support that recycles every breath and every drop of water, agriculture running under artificial light with no soil and no rain, radiation shielding that mimics a planetary magnetic field, power generation that works 1 billion miles from the sun. Each one of those systems is its own field of research. Each one has a current state, a gap between where it stands and where it needs to be, and a set of open problems that scientists are working on right now. This video is going to walk through every one of them. The question is not whether we want to do this, it is whether the physics allows it, and the answer turns out to be more complicated and more surprising than anyone who has not looked closely would guess. Every breath you take involves a machine so old and so reliable that you have never once had to think about it. Right now, somewhere between 50 and 80% of the oxygen entering your lungs was produced by organisms floating in the ocean. Phytoplankton. Microscopic, individually invisible, collectively the largest oxygen factory on the planet. The rest comes mostly from land-based plants, turning sunlight and carbon dioxide into sugar and releasing oxygen as a byproduct. Photosynthesis is not a metaphor for something Earth does. It is the actual mechanism. Every inhale you take is a transaction with a biological system that has been running without interruption for roughly 2.5 billion years. That same process is also removing carbon dioxide from the air. Plants absorb it. The oceans absorb it. Soils lock it into organic matter. Earth runs a carbon cycle so finely balanced that for most of its history, the concentration of carbon dioxide in the atmosphere stayed within ranges compatible with life. The system has a feedback structure. If CO2 rises, plants grow faster, absorbing more of it. If it falls, growth slows, releasing more. It is not a perfect regulator, but it is a remarkably stable one. Replicating even a rough version of that balance inside a sealed metal structure is one of the hardest problems in closed-loop engineering. The water cycle is equally invisible and equally staggering. Water evaporates from the oceans, rises, condenses into clouds, falls as rain, flows into rivers, soaks into groundwater, returns to the sea. The whole cycle moves roughly 505,000 cubic kilometers of water per year. For a single human being, the relevant version of this system is drink water, produce waste, and somewhere downstream, that water gets purified and returned to the cycle. Earth runs this at planetary scale and at zero operating cost. The hydrological cycle is, in engineering terms, a fully closed water recycling system with a solar-powered pump and a gravity-driven distribution network. Nothing aboard any spacecraft has come remotely close to matching it. Then there is the food system. Earth grows calories, not from stockpiles, not from stored reserves, but continuously, across roughly 1.5 billion hectares of agricultural land and an even larger area of natural ecosystems. The soil that makes this possible is not simple dirt. It is a living matrix of fungi, bacteria, invertebrates, and decomposed organic matter, a system that took millions of years to develop and that processes nutrients in cycles almost as complex as the atmosphere above it. A spacecraft cannot bring soil in that sense of the word. It has to build something that performs the same function with none of the depth or history. The radiation picture is where the scale comparisons start getting genuinely hard to absorb. Earth's magnetosphere is generated by the movement of molten iron in the outer core, roughly 1,800 miles underground, a mechanism that requires no human oversight and consumes no power budget anyone has to manage. The field it produces extends outward tens of thousands of miles into space, forming a vast protective bubble that deflects the constant stream of charged particles arriving from the Sun and from deep space beyond the solar system. Without it, the surface of this planet would receive radiation doses that would make complex life as we know it impossible. The magnetosphere does not merely reduce radiation, it redirects it entirely, bending the paths of incoming particles so they spiral around the field lines and never reach the ground. The atmosphere adds a second layer. The ozone layer sits at roughly 15 to 35 kilometers altitude. Compared to the diameter of Earth, that band is thinner than the skin of an apple wrapped around a basketball. And yet it absorbs essentially all of the sun's ultraviolet radiation in the most biologically damaging wavelength range. Remove it, and surface life would face a UV environment lethal to most organisms within years. These two systems, the magnetosphere and the ozone layer, work together without any coordination because they do not need to coordinate. They are physical structures doing what physics requires them to do. A spacecraft outside Earth's protection gets neither. Gravity is so constant that it barely registers as a feature of the environment. It keeps fluid in your legs rather than pooling in your head. It keeps your bones loaded and your muscles working against resistance. It tells your vestibular system which way is down. 6 months in orbit without it, and the human body begins to unmake itself. Bone mineral density drops. Muscles atrophy, the heart shrinks because it no longer has to pump against gravity's pull. Fluid shifts toward the head and presses on the optic nerve. Gravity is not a backdrop to human biology. It is a condition that human biology was built inside, and removing it has consequences that are slow, cumulative, and serious. The psychological dimension is the one that almost never appears in engineering discussions. Human beings did not evolve inside sealed chambers. They evolved in environments with open horizons, natural light that changes through the day and across the seasons, the sound of wind and rain, the smell of vegetation, and enough space to walk away from social tension and be genuinely alone. These are not luxuries. They are inputs to the nervous system that regulate mood, sleep, stress response, and cognitive function. The research from Antarctic overwinter stations and long-duration spaceflight shows clearly that their absence is measurable in psychological outcomes. Earth provides all of them constantly, automatically, and for free. Oxygen production, carbon removal, water recycling, food generation, radiation deflection at 2 separate scales, gravitational loading, and a sensory environment calibrated by millions of years of evolutionary pressure to match exactly what the human nervous system requires. These systems do not run independently, they are woven together. The plants that produce oxygen also regulate carbon dioxide and grow food. The water cycle that hydrates those plants also regulates temperature. The magnetosphere that blocks radiation also interacts with the upper atmosphere. Everything interlocks, and the interlocking is not incidental. It is the source of the stability. Every one of those systems has to be rebuilt from scratch the moment you leave the surface, and none of them are simple. In 1969, the year humans first walked on the moon, a physicist at Princeton named Gerard O'Neill started asking his students a question that had no obvious answer. The question was simple on its surface. Is the surface of a planet the right place for an expanding technological civilization? His students expected a quick yes. The answer, when they actually ran the numbers, was no. O'Neill was not a dreamer working outside the mainstream. He was a particle physicist with a serious reputation, someone who had designed particle storage rings and published in journals that did not tolerate loose thinking. When he turned his attention to space settlement in the early 1970s, he brought that same rigor with him. He was not asking whether humans might one day live in space. He was asking whether the specific engineering of doing so was feasible with technologies that already existed or were clearly within reach. His conclusion was that it was. Not someday in the distant future, now. With 1970s materials and 1970s rocket technology, the basic structure of a permanent human habitat in open space was achievable. The world he was working in made his question feel urgent. The early 1970s were marked by something that is easy to forget from a distance. A genuine, widespread fear that industrial civilization was running out of room. The 1973 oil embargo had made energy scarcity feel suddenly real. Population projections suggested Earth was approaching its carrying capacity. The Club of Rome's 1972 report, Limits to Growth, had landed with enormous force in scientific and policy circles. The feeling of the era was that humanity was approaching a wall, and the debate was mostly about how to slow down before hitting it. O'Neill's answer was to go around it. The problem wasn't that Earth had limits. The problem was that people were assuming civilization had to stay on Earth. His core argument was direct and physical. The surfaces of planets are actually poor locations for expanding civilization. They sit at the bottom of deep gravity wells, which makes getting material off them enormously expensive. They have fixed surface areas. Their climates and ecologies are given, not chosen. Open space, by contrast, offers something no planet can, an environment you design from scratch. You choose the gravity, you choose the climate, you choose the length of the day, you decide how much land area to build and where to put it. A planet gives you what it has. A constructed habitat gives you what you specify. This was the insight that changed the framing of the entire question. The question was not how humans could survive in space despite its harshness. The question was how humans could build habitats in space that were better than planets for supporting large populations. O'Neill believed the answer was cylinder-shaped rotating structures of enormous size, built from materials mined off the moon, positioned at gravitationally stable points between Earth and Moon. He published the idea in Physics Today in 1974. The response was immediate and serious. This was not a letter to a science fiction magazine. It was a peer-reviewed paper in one of the most read physics journals in the world, and it prompted physicists and engineers to start checking his math. NASA checked it too. In 1975, the agency co-sponsored a summer study at Ames Research Center in California, run jointly with Stanford University. Roughly 50 scientists, engineers and architects spent 10 weeks working through the detailed design of a space habitat. The group was not playing thought experiments, they were producing engineering documentation, mass budgets, structural load calculations, agricultural area requirements, power system specifications. What came out of that summer was a serious technical report with real numbers attached to every claim. The designs they developed, the Stanford Torus being the most famous, were sized for 10,000 permanent residents, with detailed plans for food production, power generation, waste recycling, and community infrastructure. O'Neill had been running a similar study group at Princeton for several years by that point. His students worked through the economics of building the first habitat using material launched by a mass driver from the lunar surface, a device that would accelerate payloads electromagnetically along a long track and fling them into space without using any rocket fuel. The mass driver was not exotic technology, it was a linear electric motor. The kind of engineering involved had close relatives in existing systems. The group calculated the cost per kilogram of material delivered to the construction site and compared it to the cost of launching the same mass from Earth. The numbers favored the lunar approach by a large margin, even accounting for the cost of establishing the lunar operation in the first place. O'Neill was not the first person to think in these terms. John Desmond Bernal, a British physicist, had sketched out the basic concept in 1929 in a short book called The World, the Flesh, and the Devil. Bernal imagined a hollow sphere roughly 10 miles across, housing 10,000 people, spinning to provide gravity, with agriculture on the interior surface and a complete internal ecosystem. The idea sat in relative obscurity for decades, mostly because the technology to do anything about it did not exist. By the 1970s, it did. O'Neill had read Bernal. He scaled the concept up, worked through the structural engineering in detail, and replaced the vague outline with something you could actually build. The ambition behind these proposals was not modest. O'Neill's full vision called for habitats housing millions of people, built in stages, with each generation of colonies providing the industrial base and workforce to construct the next. The first habitat would be relatively small, the second would be larger. Eventually, the structures would be large enough to contain entire landscapes, rivers, hills, forests, cities. The energy crisis that had helped motivate the project would be solved by solar power satellites built by the colonies and beamed to Earth. The population pressure that worried the Club of Rome would dissolve as hundreds of millions of people moved off the planet entirely. These were not casual speculations. They were conclusions drawn from calculations that any physicist could check, and many did. What they produced was not a dream. It was a blueprint, and the blueprints are still sitting in the archives, waiting. O'Neill's most ambitious design was something he called Island 3, and the numbers it required were large enough that when he first presented them, some of his colleagues assumed he had made an arithmetic error. He had not. The structure he was proposing was 5 miles in diameter and 20 miles long, a cylinder the size of a small county, rotating in open space, with people living on the inside of its curved hull. The math was correct. The ambition was simply larger than most people were prepared to process at a glance. To understand why the cylinder shape matters, you have to think about what rotation actually does to a surface. When a cylinder spins, anything on its inner wall gets pushed outward by centrifugal force. Stand on that inner surface and the force pushes you towards the hull the same way gravity pushes you towards the ground on Earth. The faster the spin and the larger the radius, the stronger the effect. O'Neill's Island 3 would rotate at roughly 1 revolution per 3 minutes, slow enough that no one inside would feel dizzy, but fast enough that the effective gravity at the inner surface would match Earth's. The cylinder shape is efficient for this purpose because the entire inner surface becomes usable living space. Every square meter of hull, from one end to the other, sits at the same radius from the central axis. Every resident experiences the same effective gravity. There are no low gravity zones near the poles or high gravity zones at the equator. The geometry solves the problem cleanly. The interior of Island 3 was not designed to feel like the inside of a container. O'Neill imagined it as a world. The inner surface was divided into 6 long strips running the length of the cylinder, alternating between 3 land sections and 3 window sections. Light enters through the windows, which run in parallel bands along the full 20-mile length. The land strips between them would hold soil, water, vegetation, and cities. Mountains could be built into the structure. Rivers could run the length of entire strips. Clouds would form naturally in the interior atmosphere, moving through a sky that was actually the far side of the same cylinder you were standing on. Look up from the surface and you would see land curving overhead, cities hanging above you, rivers glinting from what appeared to be the ceiling. The scale is large enough that the interior would feel open rather than enclosed. Standing anywhere in the habitable zone, the far end of the cylinder would be 20 miles away, beyond the threshold of easy visibility, lost in atmospheric haze. The numbers, again, the total interior surface area of Island 3 runs to several hundred square miles. Population estimates in O'Neill's original proposals reached into the millions. This was not a space station in any conventional sense. It was a city built from scratch, engineered to spec, attached to nothing. 2 of these cylinders would be built together, paired end to end and counter-rotating. This part of the design is easy to overlook but structurally essential. A single spinning cylinder acts like a gyroscope. Gyroscopes resist changes in orientation, which means a single cylinder would make steering the entire habitat extremely difficult. You could not easily point it in a new direction or maintain a stable solar orientation without fighting enormous forces. The counter-rotating pair cancels this effect. The 2 cylinders spin in opposite directions at the same rate, and their gyroscopic effects cancel each other out. The habitat can be oriented freely, maneuvered when necessary, and kept in stable alignment relative to the Sun without fighting its own momentum. Mechanically, the pair is connected by a non-rotating central hub that handles docking, transport between the 2 sections, and zero-gravity industrial facilities where no simulated gravity is needed. O'Neill's original material vision centered on the Moon. Lunar regolith contains silicon, aluminum, iron, titanium, and oxygen locked inside oxide compounds. Strip mining and processing the lunar surface to yield construction materials was not exotic chemistry, it was industrial metallurgy applied in a new location. The problem was getting the material off the Moon economically. He proposed a mass driver, an electromagnetic catapult running along the lunar surface, accelerating payloads to escape velocity and flinging them into space on a trajectory that would deposit them at a collection point in lunar orbit. The Moon's low gravity and absent atmosphere make this feasible in a way it would never be on Earth. The mass driver requires no propellant. It requires power, and the lunar surface receives constant sunlight. The economics were striking. Launching material from the lunar surface via mass driver would cost a fraction of what it costs to lift an equivalent mass from Earth against a full gravity well and through a dense atmosphere. Once the first cylinder was built, the logic became self-reinforcing. The first colony, drawing on lunar material, would build the infrastructure to construct a second colony. The second would help build a third. O'Neill saw this as genuinely self-replicating. Each generation of habitats would expand the total human presence in space without requiring proportionally larger inputs from Earth. The home planet would supply people, seeds, knowledge, and the initial equipment to get the mass drivers running. After that, the process could sustain itself. What this design offers that no planet can is control. Weather inside Island 3 is engineered. Temperature is engineered. Seasons, if the inhabitants want them, are programmed into the lighting schedule. There are no tectonic plates. There are no fault lines. There are no hurricanes forming over warm ocean water. No prolonged droughts driven by atmospheric circulation patterns nobody can predict. Anything that goes wrong inside Island 3 went wrong because a human system failed, which means a human system can fix it. The randomness and violence that define Earth's surface, the volcanic eruptions, the earthquakes, the catastrophic storms, would simply not exist unless someone deliberately built them in. The environment would be exactly as stable as the engineering that produced it. The sky above you would curve upward and eventually disappear into the far end of the cylinder, a horizon that curves the wrong way, marking the edge of a world you could walk around in a single day. NASA took O'Neill's ideas seriously enough in 1975 to convene an entire summer study at Ames Research Center. And what came out of it was not one design, but 3 competing visions for what a permanent human home in space might look like. The engineers and physicists who gathered that summer were not there to dream, they were there to calculate. And when the summer ended, they had produced detailed specifications for structures that could house thousands of people in a rotating, self-contained world, far from any planetary surface. The O'Neill cylinder was the most ambitious of the 3, but the other 2 designs were not afterthoughts. They were serious alternatives, each with its own logic, its own advantages, and its own answer to the question of what it should feel like to live in space permanently. The design that emerged most directly from that summer study was the Stanford Torus. Picture a wheel, a very large wheel. The torus has a major diameter of roughly 1.8 kilometers, and the tube itself, the part people live inside, is about 130 meters across. The whole structure rotates once per minute. That rotation generates a centrifugal force along the inner surface of the tube that closely approximates Earth's gravity. 10,000 people could live inside it. By the standards of the O'Neill cylinder, which was designed for millions, 10,000 sounds modest, but that was precisely the point. The Stanford Torus was conceived as a first step, a proof of concept at a scale that felt achievable rather than boundless. The cylinder required staggering quantities of material and a construction timeline that stretched across decades. The Torus could be built earlier, with less, and still demonstrate every principle that mattered. The interior of the Torus is not a dark corridor. Standing on the inner surface, you would look out across a curved landscape that sweeps upward on both sides before closing above your head. The land curves rather than flattens. There is no flat horizon. Farms, parks, and low buildings would line the inner surface, all of it bathed in sunlight redirected inward from mirrors positioned at the central hub. That hub sits at the rotation axis, where centrifugal force drops to zero. Zero gravity at the center becomes a resource. Solar energy collectors sit there. Docking ports for arriving spacecraft sit there. Manufacturing areas that benefit from microgravity could operate there. The hub and the torus are connected by spokes, pressurized corridors that transition gradually from zero gravity at the center to full gravity at the rim. Moving between them would be a strange physical experience, nothing like anything on Earth. The torus has one limitation that the engineers knew about and debated seriously. Standing anywhere inside the tube, you can see only a fraction of the habitat. The curve of the structure closes off your view after a short distance. Estimates suggest that from a given point, you can see less than a third of the total interior. The world visible to you at any moment is a contained arc, not a panorama. It feels enclosed in a way the cylinder does not. Whether that matters depends on the person. Some find enclosure comfortable, others find it oppressive. The engineers in 1975 treated this as a design constraint, something to be managed through interior architecture and lighting. John Desmond Burnell had a different answer entirely. Burnell was a British physicist, and in 1929, decades before anyone was actually designing space habitats, he sketched out a concept that was radical even by the standards of his time. A sphere, 10 miles in diameter, pressurized, spinning, holding tens of thousands of people on its inner surface. The version that eventually got incorporated into the NASA study was scaled down considerably. A Burnell sphere in the range of 500 meters in diameter, spinning at roughly 2 revolutions per minute, would generate close to Earth gravity at its equator. Population capacity would be in the low thousands, smaller than the torus, far smaller than the cylinder. What the sphere offers is a particular kind of openness. Stand anywhere on the inner equatorial surface of a Bernal sphere and look up. You can see the entire interior at once. The whole world is visible from a single vantage point. The far side of the sphere is above your head, curving away in every direction. It is a different perceptual experience than either the cylinder or the torus. Closer to standing inside a snow globe than anything else. Whether that is comforting or disorienting is, again, not a question engineering can settle. The sphere does score better than the torus on internal visibility. Studies that compared the three designs specifically measured the proportion of interior surface visible from a given point. For the cylinder and the sphere, that proportion is essentially 1. The whole habitat is available to the eye. For the torus, it falls below 1/3. That gap is not trivial. Humans are spatial creatures. The psychological weight of being able to see far, of knowing what is around you, of having visual range, does not disappear just because you are in a machine rather than a meadow. The structural trade-offs between the three designs are real and important. The sphere is the most efficient shape from a pure materials standpoint. The sphere encloses the maximum volume for a given surface area, but the torus allows simpler construction in stages, section by section, and its geometry makes it easier to expand or repair than a sealed sphere. The cylinder is largest and most complex but offers the most livable surface area per unit of structural mass at scale. Each design also implies a different experience of community. 10,000 people in a torus live in a long curved tube where the edges of their world disappear around a bend. Several million in a cylinder live under a sky that curves up and over their heads. A few thousand in a sphere live in a world they can see from end to end all at once. Those differences are not decorative. They shape how people relate to their surroundings, how they understand their own position, and what kind of society they build. The choice between them was never purely technical. It was also about what kind of world you wanted to live in, which turns out to be a harder question than the engineering. 6 months aboard the International Space Station will cost you roughly 1 to 2% of your bone density per month in the spine and hip, and some of that loss does not come back. That is not a side effect. That is not a minor inconvenience to be managed with supplements. That is your skeleton quietly dissolving in response to an environment it was never designed to handle. The human body built its bones under gravity. It maintains them under gravity. Remove the gravity, and the body reads the situation as a signal that all that dense, heavy tissue is unnecessary weight, and it begins to discard it. This is what microgravity actually does to a person, and it is worth sitting with before moving on to the engineering solution, because the problem is more comprehensive than most people realize. Bone loss is the headline, but it is only one item on a long list. Muscle tissue atrophies at a similar rate. Without the constant low-level effort of standing upright and moving against gravity, the muscles responsible for posture, balance, and locomotion simply shrink. Astronauts on 6-month ISS missions lose measurable mass in their leg muscles, their lower back, and their core. The cardiovascular system changes as well. On Earth, the heart works against gravity to push blood upward from the legs. In weightlessness, that load disappears. The heart adapts by becoming smaller and less efficient, a change that creates real problems when the astronaut returns to a gravitational environment and the demand suddenly returns. Fluid redistribution is another consequence, and it is one of the stranger ones. Without gravity pulling fluids toward the lower body, those fluids shift upward. Astronauts in microgravity develop what is colloquially called puffy face and bird legs, fluid pooling in the upper body while the lower limbs thin out. More seriously, the intracranial pressure increases as cerebrospinal fluid redistributes toward the head. This increased pressure is now understood to be behind the visual impairment that a significant number of long-duration astronauts experience. The eyeball itself can change shape. The optic nerve can swell. Some astronauts return from the ISS needing different eyeglass prescriptions than when they left. A small number show structural changes that persist. For a mission lasting not 6 months but 6 years or 60 years, the implications are severe. The immune system behaves strangely in microgravity as well. Latent viruses that the immune system normally keeps suppressed, including certain herpes viruses, reactivate during spaceflight. Immune cell function changes. The body is not simply experiencing a neutral environment, it is experiencing a wrong one its evolutionary history gave it no preparation for. Every physiological system in the human body was calibrated over millions of years for a specific gravitational load. Take that load away, and system after system begins to drift out of specification. So the engineers building a second Earth spacecraft cannot treat gravity as optional. It is not a comfort feature, it is a medical requirement. And this is precisely the problem that the rotating habitat designs described earlier were engineered to solve. When a structure rotates, anything on its inner surface experiences a centrifugal force pushing outward from the axis of rotation. Stand on the inner surface of a spinning cylinder, and that outward push feels exactly like being pressed against the floor by gravity. The biology does not know the difference. The bones load, the muscles work, the fluids stay in the legs where they belong. The physics of this is clean and calculable. The effective gravitational force at any point on the inner surface of a rotating structure depends on 2 variables, the radius of the structure and its rotation rate. A larger radius at a given rotation rate produces a stronger effective gravity. A faster rotation rate at a given radius does the same. The equation is simple enough that you can work out the numbers on a piece of paper. To produce 1 full Earth gravity, a structure with a radius of 224 meters needs to rotate approximately twice per minute. A structure with a radius of 900 meters needs to rotate just once per minute. Here is why the radius matters enormously beyond just the math. When the rotation rate is high, the Coriolis effect becomes perceptible to the people living inside. The Coriolis effect is what happens when something moves within a rotating reference frame. The path of motion appears to curve relative to the surface. In a fast-spinning habitat, this manifests as dizziness when you turn your head quickly, nausea when you try to move in certain directions, and a persistent sense of spatial disorientation that the brain cannot fully adapt to. The faster the spin, the worse the effect. Early proposals for small rotating compartments aboard conventional spacecraft ran into this problem immediately. A pod 10 meters in radius would need to spin extremely fast to generate useful gravity, and anyone inside would feel profoundly unwell. O'Neill understood this when he was designing his cylinders. His answer was to make the structures large enough that the rotation rate required for full gravity became slow enough to be imperceptible. At the scale of Island 3, with a radius of roughly 3.2 kilometers, the rotation rate for 1 Earth gravity is less than 2 revolutions per minute. The Coriolis effect at that speed is so small that it falls below the threshold of human perception. The inhabitants would have no sense of rotation at all. They would simply feel weight, exactly as they do on Earth. The minimum viable radius for a tolerable rotating environment is generally estimated at somewhere above 200 meters, with most researchers preferring 500 meters or more as a comfortable working threshold. Below 200 meters, even with careful engineering, the Coriolis effects become difficult to suppress. Above 500 meters, they become essentially negligible. The ISS has conducted limited experiments in partial gravity to try to establish what threshold of gravitational load is actually required for long-term health, since full Earth gravity may not be strictly necessary. The data suggests that even partial gravity, perhaps 1/3 to 1/2 of Earth normal, may preserve most of the critical physiological functions. If that holds up, the radius requirements for a livable rotating structure come down considerably. But even at those reduced thresholds, you are still talking about a structure several hundred meters across, and most likely much larger. The physics of spinning a structure is well understood. It is the same physics that flings water out of a salad spinner, and it has no theoretical barriers, only the practical challenge of building something large enough to make it comfortable. Earth has a radiation problem, and it solved it a long time ago with a trick that cost nothing and required no maintenance, a magnetic field generated by a spinning iron core 1,800 miles underground. That field extends tens of thousands of miles out into space. It wraps around the planet in an invisible cocoon, bending the paths of incoming charged particles, deflecting the most dangerous ones before they ever get close to the surface. What does not get deflected gets absorbed. The atmosphere, 60 miles of thickening gas, catches whatever slips through and breaks it apart before it reaches anything alive. You have never had to think about any of this. The planet handled it before your species existed. The moment you leave, it stops. There are 3 categories of radiation waiting for anything that ventures beyond Earth's protection. The first is galactic cosmic rays. These are not rays in the sense of light or heat. They are individual atomic nuclei, stripped of their electrons and accelerated to near-light speed by supernova explosions somewhere across the galaxy. They arrive from every direction simultaneously, day and night, without pause. They carry so much energy that they pass straight through ordinary matter like bullets through paper. A proton traveling at 99.9% the speed of light does not stop for aluminum walls. It does not stop for water. It keeps going, and as it goes, it strips electrons from the atoms in whatever it passes through, including the atoms in human tissue, including the atoms in DNA. The second category is solar energetic particle events. These are sudden, violent eruptions from the sun, coronal mass ejections that release enormous quantities of high-energy protons in a matter of minutes. On Earth, you see them as geomagnetic storms, occasionally disrupting satellites or power grids. In deep space, without the magnetosphere blocking the front door, a major solar particle event is a medical emergency. Crews would need a heavily shielded storm shelter. They would need warning. They would need to get inside it fast. The third category is the Van Allen belts themselves, 2 donut-shaped zones of trapped radiation surrounding Earth, held in place by the very magnetic field that protects the surface. Crossing through the outer belt during a departure from Earth orbit gives any spacecraft a measurable dose. Apollo crews pass through them quickly enough to keep the exposure manageable. A ship that lingers would not be so lucky. Here is what the numbers look like in practice. An astronaut on the International Space Station receives a radiation dose of roughly 150 to 200 millisieverts per year. That sounds abstract until you compare it to life on the ground, where the average person receives about 3 millisieverts annually from all sources combined. ISS astronauts are getting somewhere between 50 and 70 times the surface dose. Even so, the station sits inside the magnetosphere's partial protection. It is not a fair test of what deep space does to a human body. Beyond the magnetosphere, the numbers get worse. NASA's estimates for a Mars transit mission put the crew dose at somewhere between 300 and 600 millisieverts for the journey alone, depending on where the sun is in its activity cycle. A 6-month flight each way means a round trip could expose the crew to more than 600 millisieverts before they have spent a single day on the Martian surface. That crosses the threshold that most regulatory agencies consider the upper limit of acceptable lifetime occupational exposure for radiation workers on Earth. And that is before accounting for the surface mission itself. On the surface of Mars, the dose is roughly 30 times higher than on Earth's surface. Mars has no magnetosphere. Its atmosphere is less than 1% as dense as Earth's. Neither protection works. The Curiosity rover's radiation detector measured a surface dose equivalent to about 0.7 millisieverts per day at Gale Crater. For a crew spending 18 months on the surface while waiting for a launch window back to Earth, that accumulates into a number that carries a measurable increase in lifetime cancer risk. The biological consequences are not limited to cancer. Galactic cosmic rays are heavy ions, and heavy ions do something that X-rays and gamma rays do not. They travel in straight lines through tissue, leaving dense tracks of damage behind them. When that track passes through the lens of an eye, it can trigger cataracts. When it passes through neurons in the brain, the damage does not repair the way other tissue damage does. Studies on rodents exposed to simulated galactic cosmic ray doses have found measurable impairment in memory, attention, and the ability to reverse learned behaviors. The term researchers use is central nervous system damage, and it is not a theoretical concern. It is something the data already suggests is happening at the doses a Mars crew would receive. What makes this particularly difficult is the nature of galactic cosmic rays themselves. They are not a beam you can hide from by pointing the ship in the right direction. They come from everywhere. Shielding that surrounds the crew on all sides is the only option, and the mass requirements for that shielding are the problem that defeats conventional approaches. Hydrogen-rich materials stop radiation more efficiently than metals because hydrogen nuclei are close in mass to the incoming particles, absorbing more energy per collision. Polyethylene works better than aluminum by a significant margin. Water works well, but to meaningfully reduce the galactic cosmic ray dose, you need meters of water or polyethylene surrounding the entire crew compartment. The mass of material required runs into hundreds of tons for a habitat of any reasonable size. Launching that mass from Earth's surface, at current launch costs, is economically impossible. Even if cost were no object, the structural challenge of encasing a crewed habitat in meters of shielding material while keeping the overall spacecraft mass within the limits of any feasible propulsion system is a problem with no clean solution. There is also a secondary effect that makes the situation worse. When high-energy particles hit heavy nuclei in a thick shield, they produce secondary radiation, a spray of neutrons and lighter particles that can be more damaging to tissue at close range than the original particles were. Too thin a shield reduces the dose slightly. Too thick a shield built from the wrong material can actually increase the biological damage. The physics of passive shielding is not simply a matter of adding more material and watching the dose fall. The mathematics of passive shielding against galactic cosmic rays is brutal. You need so much material that by the time you have protected your crew, you've also built something too heavy to launch from Earth's surface in any practical sense. The reason Earth's magnetic field works as radiation shielding is not that it absorbs the radiation, it is that it deflects it, bending the paths of incoming charged particles so they never reach the surface. This distinction matters enormously. Absorption requires mass, deflection requires a field, and a field, if you can generate it strong enough, weighs almost nothing compared to the tonnage of water or polyethylene you would otherwise need to stack around your crew. Earth's magnetosphere extends roughly 60,000 kilometers toward the Sun and stretches hundreds of thousands of kilometers in the opposite direction, forming a colossal magnetic bubble in space. The field is generated by convection currents of liquid iron moving deep in the planet's core. It deflects the overwhelming majority of galactic cosmic rays and solar energetic particles before they get anywhere near the atmosphere. What the magnetosphere doesn't catch, the atmosphere handles. The result is a radiation environment on the surface that human biology has lived with comfortably for millions of years. Strip both of those layers away and you have deep space, which is something else entirely. The question researchers started seriously asking in the late 1990s and early 2000s was whether a spacecraft could carry its own magnetosphere. Not a planet's worth of one, a scaled, engineered version, strong enough to push incoming charged particles wide of the hull without requiring the mass of a small moon to operate. The European Space Agency funded a series of studies on this concept. University groups in Portugal, the United Kingdom, the United States began modeling the minimum field strengths that would actually protect a crew against galactic cosmic rays on a transit to Mars. What those models showed was encouraging and challenging in equal measure. The most studied engineering approach involves superconducting electromagnets arranged in a toroidal configuration around the spacecraft. A torus shape, essentially a ring or donut geometry, creates a shielded interior region where the magnetic field lines converge in a way that is relatively free from the field itself. The crew lives in that interior region. Incoming charged particles, following curved paths through the magnetic field, are bent away from the protected zone before they reach the hull. The geometry is not perfect. There are directions from which particles can still penetrate, and no configuration eliminates the risk completely. But the models suggest that a well-designed magnetic shield could reduce the galactic cosmic ray dose by a significant fraction, enough to push lifetime exposure back into a range that is at least comparable to what a career airline pilot receives over many years, rather than something that causes measurable cognitive damage on a single voyage. The mass comparison is stark. To shield a crew module against galactic cosmic rays using passive water shielding to the point of meaningful dose reduction, you are looking at hundreds to thousands of metric tons of shielding material. The numbers vary depending on the target dose level, but the physics is unforgiving. High-energy galactic cosmic rays do not stop easily. Getting them down to acceptable levels passively requires depths of material that are simply incompatible with any realistic launch architecture. A superconducting magnetic shield system capable of comparable protection, by contrast, has been estimated in various studies to weigh on the order of tens of metric tons for the magnet infrastructure. The difference is an order of magnitude. On a mission to Mars or beyond, that difference is the mission. The challenges are real and they are not small. Superconducting magnets operate near absolute zero, typically around 4 Kelvin, which is roughly negative 269 degrees Celsius. The crew habitat they are protecting operates at roughly 295 Kelvin. Managing that thermal gradient on a spacecraft, keeping the magnets cold while the interior stays warm, is a significant engineering problem. Cryogenic systems require power to maintain. They have failure modes. If a superconducting magnet quenches, loses its superconducting state suddenly, it can release its stored magnetic energy in a rapid and potentially damaging discharge. The structural forces the magnets exert on each other and on the spacecraft frame are also extreme. A strong enough magnetic field generates enormous mechanical stresses. The structure holding the magnets in place has to withstand those forces continuously for years. Then there is the power requirement. Generating and maintaining a field strong enough to deflect galactic cosmic rays demands a continuous power draw that a solar-powered spacecraft in the outer solar system cannot easily provide. This is why magnetic shielding discussions often appear alongside discussions of nuclear power or fusion propulsion. The two problems point toward the same solution. There is a complementary approach worth noting: plasma shielding. Surrounding the spacecraft with an ionized gas cloud held in place by a weak magnetic field has been studied as an additional layer of protection. A plasma envelope can interact with incoming particles and scatter them before they reach the magnetic field proper. It adds complexity but potentially allows for a weaker primary magnet to achieve the same protective effect. The development that offers the most genuine optimism is the progress in high-temperature superconductors. For most of the 20th century, superconductivity required cooling to temperatures close to absolute zero, demanding liquid helium systems that were bulky and high maintenance. Over the past 2 decades, materials have been developed that superconduct at temperatures achievable with liquid nitrogen. That is far cheaper and easier to manage. More recently, research groups have pushed the threshold higher still. If superconductors that function at tens of Kelvin or eventually at higher temperatures can be produced in the form needed for large electromagnets, the cryogenic demands of a spacecraft magnetosphere drop dramatically. The power requirements shrink. the thermal management problem becomes tractable. No full-scale test has yet been conducted in space. Laboratory demonstrations have confirmed the underlying physics. Computer models have mapped the field geometries. Small prototype magnets have operated in the relevant configurations. But the jump from a laboratory demonstration to a system rated for years of continuous operation on a crewed deep space spacecraft is a long jump. Nobody has made it yet. The technology exists in principle. The physics is solid. The advantages over passive shielding are dramatic. But the engineering gap between a laboratory demonstration and a working system on a spacecraft is still very wide. The water you drank this morning has been on this planet for billions of years, passing through oceans, clouds, glaciers, rivers, and the bodies of countless organisms, and it arrived at your tap because Earth runs a closed loop so efficient it never needs to be recharged. Nothing is lost. Nothing is vented. Every molecule cycles back into the system eventually, driven by solar energy and the slow grind of planetary chemistry. That is the standard a second Earth spacecraft has to meet. Not approximate it, not get close, meet it, because the moment you fall short, you are on a countdown, and in deep space, countdowns you cannot stop tend to end badly. The terminology here matters. A closed-loop life support system is one where every output from a human body or a piece of machinery becomes an input somewhere else in the system. You exhale carbon dioxide. The system captures it and converts it back to oxygen. You produce urine. The system processes it back into drinkable water. You generate biological waste. The system breaks it down into nutrients that feed the next cycle. Nothing leaves. The International Space Station gives us the clearest picture of where this technology stands right now, and the picture is genuinely impressive, but not yet enough. The ISS runs a system called the Environmental Control and Life Support System, and its water recovery capabilities are remarkable by any engineering standard. Urine gets processed through a urine processor assembly, then through a water processor, and comes out the other side as clean drinking water. Humidity pulled from the cabin air gets condensed and added to the same recovery stream. Current recovery rates sit somewhere between 90 and 95% of all water used aboard the station. That number represents decades of refinement and is genuinely extraordinary. Oxygen is generated through electrolysis, running electrical current through water to split it into hydrogen and oxygen, with the oxygen released into the cabin atmosphere and the hydrogen vented overboard. Carbon dioxide is captured by chemical scrubbers, absorbed into materials that either regenerate through heating or are eventually replaced. Here is the gap. None of that describes a closed loop. It describes a very efficient open loop. The hydrogen vented overboard is lost. The chemical scrubbers require replacement materials. The water recovery system loses a few % every cycle, which adds up fast. A resupply ship arrives at the ISS roughly every few months, carrying replacement chemicals, spare components, backup oxygen, and additional supplies. Pull that resupply away, and the station's life support systems would begin failing within months. For a mission to Mars, the nearest resupply is 8 months away at minimum. For anything beyond that, resupply is not a contingency plan. It is not a plan at all. This is the problem that the European Space Agency has been working on since the 1980s through a program called MELISA. The name stands for Micro-Ecological Life Support System Alternative, and the ambition behind it is much larger than the acronym suggests. MELISA is an attempt to build a life support system out of living biology rather than chemical engineering, to replace the scrubbers and processors with something closer to what Earth actually uses, which is organisms. The logic is straightforward. Bacteria, algae, and plants do not need resupply. They reproduce, they repair themselves. Given the right conditions and the right nutrients, they keep running indefinitely. That is exactly the property you need. The MELISA loop works in stages. Organic waste from the crew, food scraps, fecal matter, inedible plant material, enters a bioreactor containing thermophilic bacteria, microorganisms that thrive at high temperatures. These bacteria break the waste down into simpler compounds: ammonia, carbon dioxide, minerals. That output flows into a second reactor where a different set of bacteria converts the ammonia into nitrates. Those nitrates, combined with the carbon dioxide and light, feed a compartment full of algae, specifically spirulina and other cyanobacteria, which photosynthesize, absorbing the carbon dioxide and producing oxygen. The algae also serve as a food source. The treated liquid feeds into a plant growth compartment where higher plants like wheat, lettuce, and other crops absorb the remaining nutrients and produce food for the crew. The crew eats, breathes the oxygen the plants produced, and generates the waste that starts the cycle again. Every stage feeds the next. Nothing exits the loop. ESA currently operates a pilot plant for Melissa in Barcelona, and that facility has kept populations of rats alive in a sealed biological loop. That is not a trivial achievement. Keeping any complex organism alive in a completely sealed ecosystem for extended periods requires the loop to stay balanced, the organisms to stay healthy, and the entire system to resist the many ways that closed biological systems can collapse. The Barcelona facility represents 30+ years of incremental progress and stands as the most serious attempt anywhere on Earth to engineer a true biological closure. The contamination problem is one of the most serious obstacles. In an open system, a bacterial infection is a contained event. You treat it, resupply what was lost, move on. In a closed biological loop, a pathogen introduced into one compartment has nowhere to go but further into the loop. An aggressive organism that outcompetes the carefully selected algae or disrupts the bacterial processing stages does not just create a local problem, it unravels the entire cycle. Melissa's compartmentalized design provides some protection. Each stage is physically separated, and microorganisms from one stage are not supposed to migrate freely into another. But the sterilization requirements are demanding, and the risks compound over time. The longer the mission, the more chances for something to go wrong. Then there is the mathematics of closure itself. A 95% recovery rate sounds nearly perfect. Run it forward. On a 3-year mission with a crew of 6, that 5% loss accumulates every single day. Water that is not recovered must come from somewhere. Oxygen that is not regenerated must be replaced. The massive backup supplies required to cover a 5% loss over 3 years is enormous. Now consider what 99.9% recovery looks like by comparison. The same calculation produces a loss rate 100 times smaller. The gap between those two numbers is not an incremental engineering improvement. It is the difference between a mission architecture that is viable and one that requires a resupply chain that does not exist. Getting from 95% to 99.9% sounds like a minor improvement, but on a mission lasting 3 years, the difference between those two numbers is the difference between a crew that survives and a crew that slowly runs out of everything it needs. The caloric math for keeping a crew of 8 alive on a multi-year mission to Mars without any resupply from Earth works out to roughly the agricultural output of a well-designed greenhouse the size of a large house. That number sounds manageable until you start adding up everything a plant actually needs to grow. Then you realize why food production is the part of the closed-loop problem that keeps agricultural engineers awake at night. Oxygen recycling is hard, water recovery is hard, but feeding people continuously from scratch inside a sealed metal structure moving through a vacuum is in a different category of difficulty entirely. Plants are not simple machines. They need light at the right wavelength and the right intensity. They need water delivered to their roots in precise quantities. They need nutrients, nitrogen, phosphorus, potassium, a list of trace minerals that goes on longer than most people expect. They need carbon dioxide, which a crew conveniently produces, but in concentrations that have to be carefully managed. They need temperature stability. They need gravity, or at least a reasonable approximation of it. Roots grow in response to gravitational cues. In true microgravity, without careful engineering, water pools around roots and drowns them rather than draining away. Each of those requirements is a system that can fail, and all of them have to work simultaneously, continuously, for years. NASA has been working on this seriously since the 1980s. Kennedy Space Center operated its biomass production chamber from the late 1980s through the year 2000. But because volume efficiency was a hard constraint, in space, every cubic meter costs something. A flat field is the least efficient possible use of that space. The veggie growth chamber currently operating aboard the International Space Station is a more recent chapter in this story. Veggie is compact, roughly the size of a carry-on bag, and it has produced successful harvests of red lettuce, green lettuce, radishes, kale and mustard greens. Astronauts have eaten crops grown in orbit. That demonstrated that plants will grow in microgravity under artificial light, that the food is safe to eat. But the psychological effect on crew members of tending living plants and then consuming them is measurable and positive. NASA's Ohalo 3 project is the current ambition, a prototype operational crop production system designed for the Lunar Gateway and eventually for a Mars transit vehicle. The reason hydroponics dominates all serious thinking about space agriculture is not complicated. Soil is heavy. Moving a kilogram of topsoil from Earth's surface to deep space carries a cost that makes the entire concept impractical at any meaningful scale. Hydroponics eliminates the soil entirely, replacing it with a water and nutrient solution delivered directly to the root zone. The advantages compound quickly. Nutrient concentrations can be monitored and adjusted in real time. Water use drops by roughly 90% compared to conventional farming because nothing evaporates into open air and runoff is collected and recirculated. Growth rates often increase because the plant never experiences nutrient deficiency or drought stress. The system is also modular. Racks of growing trays can be stacked vertically, multiplying the effective growing area within a given floor footprint. That is why the Kennedy Space Center engineers arrived at vertical farming independently decades before it became a concept discussed in cities on Earth. Aeroponics takes the logic one step further. Instead of submerging roots in a nutrient solution, aeroponics suspends the roots in air and mists them with nutrient-laden water at precise intervals. Root oxygenation improves. Water consumption drops further still. NASA has tested aeroponic cultivation of sweet potatoes and other crops with results that consistently outperform soil-based equivalents. The engineering challenge is the misting mechanism itself, moving parts in a space environment that must function without failure for years. But the performance advantages are significant enough that serious space agriculture proposals continue to pursue it. Not all crops are equally useful in a space context. The crops that earn their growing area are the ones that provide dense nutrition per square meter. Wheat delivers complex carbohydrates and protein and grows in relatively compact vertical configurations. Potatoes and sweet potatoes provide high caloric density and important vitamins in a crop that responds well to controlled hydroponic conditions. Soybeans are among the most nutritionally complete plant foods available, providing protein, fat, a range of micronutrients that would otherwise require animal products to supply. Microgreens, the young seedlings of various plants harvested within 1 to 2 weeks of germination, deliver concentrated nutrients in a very short growth cycle, them extremely efficient by the metric of nutrition per day per square meter. A well-designed space farm would grow all of these in rotation, managing the harvest schedule so that some crop is always ready to eat. Then there are algae and cyanobacteria. These are not crops in the conventional sense. But in a space life support system, they may be more important than any plant. Spirulina and chlorella, two cyanobacteria already consumed as food supplements on Earth, can be cultivated in dense liquid cultures that produce protein, vitamins, and oxygen simultaneously. Their growth rates are extraordinary compared to conventional crops. A cyanobacteria cultivation loop absorbs carbon dioxide, produces oxygen through photosynthesis, yields a harvestable biomass that is roughly 60 to 70% protein by dry weight. In the Melissa life support loop developed by the European Space Agency, algae occupy a central position precisely because they bridge the gap between waste processing and food production in a single biological step. The caloric numbers are worth sitting with for a moment. A moderately active adult requires roughly 2,000 to 2,500 calories per day to maintain body weight. In a well-optimized hydroponic system, producing that many calories continuously requires somewhere between 20 and 40 square meters of growing area per person. For a crew of 8, that is 160 to 320 square meters of productive growing surface. Inside an O'Neill cylinder or a structure of comparable scale, that area is not a significant fraction of the total interior. Inside a small spacecraft, it is the dominant architectural constraint. The habitat has to be built around the farm, not the other way around. What makes this more than an agricultural problem is the way a space farm is embedded in every other system on the ship. Plants absorb carbon dioxide and release oxygen. The same carbon dioxide the crew exhales, the same oxygen the crew breathes. Plants process nitrogen and phosphorus from treated wastewater, drawing nutrients out of the waste stream and locking them into edible biomass. The water that evaporates from plant leaves is recovered by the humidity condensation system and returned to the water supply. The growing chambers are warm and humid. That warmth and humidity can be managed as part of the ship's overall thermal regulation. Nothing in this system operates in isolation. In a properly designed system, the farm is not a separate department. It is the lung of the ship, the water filter, the dinner table all at once. Water in a space habitat is not one resource. It is at least 4, and the most interesting of its jobs is not keeping the crew hydrated. The crew drinks it, grows food in it, and shelters behind it. It can be split apart by electricity into 2 of the most useful gases a spacecraft could possibly carry. Each of those roles is critical on its own. Together they make water the single most consequential material any deep space habitat would need to manage. Start with the obvious job. A human being needs roughly 2 liters of drinking water per day at minimum, more under physical exertion, more again when you account for food preparation and basic sanitation. For a crew of 8 on a 3-year mission, that is a number that begins to feel serious very quickly. Now add the water required for hydroponics. The agricultural section described in the previous chapter needs continuous water input to keep crops alive, even accounting for the efficiency gains that hydroponic systems provide over soil-based farming. Water runs through nearly everything the life support system does, and the only way to make that sustainable is to get almost all of it back. This is where water recovery systems come in. The International Space Station currently runs a water recycling architecture that pulls moisture from multiple sources: cabin humidity, crew urine, and condensation from the atmosphere processing equipment. Urine goes through a distillation processor that uses heat and vacuum to separate the water from dissolved waste products. The recovered liquid then passes through a series of chemical filters and catalytic reactors before it is safe to drink again. The system achieves roughly 90 to 95% recovery on a good day. That number sounds impressive. For a short mission, it is. This distinction demands your careful attention. A 95% recovery rate means that 5% of your water disappears into waste streams every cycle. On the ISS, resupply flights top that off every few months. On a ship years from Earth, there are no resupply flights. Every fraction of a percent you fail to recover compounds across hundreds of thousands of cycles. The gap between 95% recovery and 99% recovery is not a minor engineering refinement. It is the difference between a system that slowly bleeds out and one that can sustain itself indefinitely. Getting to true closure requires better chemistry, better filtration, and biological systems that can handle the waste streams conventional hardware cannot process cleanly. That is part of why the agricultural layer matters so much. Plants absorb water, transpire it back into the air, and the humidity recovery systems catch it again, adding a biological recycling loop that complements the mechanical one. Water also has a job that most people do not immediately think about. It is one of the best radiation shielding materials available at a reasonable mass. The hydrogen atoms in water molecules are effective at absorbing and scattering the energetic particles that make deep space dangerous. The idea of water walls, panels surrounding the crew habitat filled with the habitat's reserve water supply, turns a passive storage problem into an active protective layer. The water sitting in those panels is doing two things simultaneously. It is waiting to be used, and it is absorbing radiation that would otherwise reach the crew. That is the kind of engineering elegance a self-sustaining spacecraft requires at every turn. One resource doing three jobs at once. And then there is the chemical job. Water is two hydrogen atoms bonded to one oxygen atom. Run an electrical current through it, and those bonds break. You get hydrogen gas and oxygen gas. Oxygen feeds the life support system, supplementing what the plants produce. Hydrogen and oxygen together, stored under pressure, are the most energetically dense chemical rocket propellants ever used in operational spaceflight. The engines that sent Apollo astronauts to the moon burned liquid hydrogen and liquid oxygen. A spacecraft that can produce its own propellant from water it mines locally is a spacecraft that does not need to carry its return fuel from Earth. That single capability transforms the economics of deep space exploration more dramatically than almost any other technology. Which brings the question into focus: where does the water come from in the first place? For a habitat that intends to remain self-sustaining over years or decades, the initial supply cannot simply be launched from Earth. The mass penalty is prohibitive. There is a better answer, and it has been confirmed by multiple missions over the last 2 decades. The moon has water ice, not as flowing liquid, not as surface frost, but locked in the permanent shadows of craters near the lunar poles, where sunlight has never reached in billions of years. Temperatures stay low enough to preserve ice indefinitely. The LC Ross mission in 2009 confirmed this directly. NASA deliberately crashed a rocket stage into one of these shadowed craters and analyzed the debris plume. Water was there. Multiple subsequent orbital missions have mapped the distribution and estimated the scale. The deposits are not trivial. Billions of tons of ice are sitting in those craters, waiting. C-type asteroids offer another reservoir. These are among the most common asteroid types in the solar system, and they contain hydrated minerals, water chemically bound into the rock structure. Heat the rock enough and the water releases. A single mid-sized C-type asteroid could hold more water than any single mission would ever need, and the outer solar system is full of them. The technology to extract that water and process it is not fundamentally different from industrial heating and condensation processes already well understood on Earth. A ship that carries its water from a home planet is a ship on a countdown. Every leak, every inefficiency, every failure in the recycling loop brings the mission closer to its end. A ship that can reach out and mine water from the environment around it operates on an entirely different logic. The resource becomes renewable rather than finite. The mission duration stops being limited by the size of the tank you launched with. A ship that can find its own water is a ship that can stay out there indefinitely, and the solar system turns out to be full of water, frozen and waiting, if you know how to look. Launching a kilogram of material from the surface of Earth to low orbit costs roughly as much as sending it across a continent by airplane, and then you still have to get it from low orbit to wherever you are actually going. That second leg, from low orbit to the Moon to Mars to the outer solar system, costs more again. The energy budget compounds with every kilometre. Every bolt, every panel, every litre of water, every gram of food that goes into a space habitat has to survive this process before it ever reaches space. When you start adding up the mass of a habitat capable of supporting thousands of people for decades, the numbers stop being numbers and start being arguments against the whole project. There is only one serious answer to that argument, and it has a name. In situ resource utilization, ISRU, the practice of finding what you need where you are, rather than carrying it from where you started. The logic is almost aggressively simple. Earth's gravity well is deep. Escaping it costs roughly $1,000 to $10,000 per kilogram, depending on which rocket you are using. SpaceX's Starship is pushing that number down, but even at the low end, the economics of lifting construction material from Earth's surface into space and then moving it further outward are punishing. A single O'Neill cylinder, at the scale O'Neill envisioned, would require millions of tons of structural material. Launching that from Earth is not an engineering problem. It is a financial impossibility. But lifting it from the Moon, where gravity is 1/6 as strong and there is no atmosphere to fight through, is a different calculation entirely. Lifting it from an asteroid already drifting in open space is different still. Once material is already in space, moving it costs a fraction of what it costs to get it off a planet. The Moon is the obvious starting point. Lunar regolith, the loose fragmented rock covering the surface, contains silicon, aluminum, iron, titanium, and oxygen in enormous quantities. These are not exotic materials. Silicon is the basis of glass and solar panels. Aluminum and titanium are structural metals. Iron is structural metal. Oxygen locked into oxides in the regolith can be extracted through several processes and used directly for life support. The Moon is essentially a stockpile of space habitat construction materials, sitting a few days of travel from Earth, without an atmosphere or strong gravity making extraction expensive. What was missing, until recently, was a demonstrated method for getting the oxygen out efficiently. Researchers have developed a process using molten salt electrolysis that extracts oxygen directly from lunar regolith, with significantly higher efficiency than earlier methods. The regolith is dissolved in a molten salt bath, and electrolysis separates the oxygen from the metallic oxides. The metallic byproducts, aluminum, iron, titanium, are not waste. They are the structural materials you needed anyway. One process produces both the oxygen for life support systems for lunar missions by more than 20%, and that figure will improve as the technology matures. Mars has its own version of this story. The Martian atmosphere is thin, cold, and mostly carbon dioxide. Not exactly hospitable, but the Perseverance rover is carrying an experiment called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment. And in 2021 it produced oxygen directly from that carbon dioxide atmosphere. The amounts were small, about 10 grams per hour. That is enough to demonstrate the principle, not enough to supply a habitat. But a scaled-up version of the same technology, running continuously, could supply meaningful quantities of oxygen for both life support and rocket propellant. Carbon dioxide plus electricity becomes oxygen plus carbon monoxide. The carbon monoxide is not wasted. It can be combined with hydrogen to produce methane, which is a rocket fuel. Mars can supply the oxidizer and potentially the fuel for the return trip, sourced entirely from the air outside the habitat door. Then there are the asteroids. This is where the scale becomes genuinely hard to hold in your mind. The asteroid belt contains hundreds of thousands of objects ranging from gravel to small worlds. Metallic asteroids, the M-type class, are essentially drifting masses of iron and nickel with concentrations of platinum group metals that would represent extraordinary value by any Earth-based standard. A single medium-sized metallic asteroid, something in the range of a kilometer across, contains more iron than has been extracted in all of human history combined. The platinum group metals in that same asteroid, metals that on Earth require enormous effort to mine from deep geological deposits, are present in concentrations that dwarf anything accessible on the surface of our planet. Carbonaceous asteroids, the C-type class, tell a different story, but an equally important one. These objects contain carbon, nitrogen, water-locked in hydrated minerals, and organic compounds. They are essentially the chemical feedstock for life. Carbon and nitrogen are critical for agriculture and life support. The water content, as discussed in the previous section, can be extracted by gentle heating and used directly or split into hydrogen and oxygen. The organic compounds can supplement biological systems. A carbonaceous asteroid is not just a rock, it is a supply depot that someone else built over the first few billion years of the solar system's history. What ISRU changes, fundamentally, is the relationship between the habitat and its environment. A spacecraft that carries everything it needs from Earth is a closed container with a finite lifespan. When the supplies run out, the mission ends. The supplies always run out. A spacecraft equipped to process and use the materials it encounters on its journey is operating on a different principle entirely. It is not consuming a fixed store. It is drawing on a resource base that extends across the solar system. Structural repairs can be made with locally sourced metal. Propellant can be manufactured from asteroids or planetary atmospheres. Life support consumables can be replenished from water, ice, and carbonaceous material found along the route. This is not a small distinction. Every previous spacecraft in human history has been the first kind, a container with a finite supply. The second kind has never been built. It is the technological threshold that separates a long-duration expedition from something that does not have a predetermined end date. A spacecraft that can stop at an asteroid and come away with the materials for its next 6 months of operation is not a spacecraft in the traditional sense. It is something closer to a traveling town. A spacecraft trying to be a second Earth is also trying to be a power plant, a water utility, a food production facility, and a climate control system all at once. And the energy bill for running all of those simultaneously is not trivial. But everything else demands a continuous supply of power. The lights over the hydroponic farms have to run on a cycle carefully timed to match plant biology. The water processors never stop. The CO2 scrubbers run around the clock. The habitat has to be kept warm against a background temperature of minus 270 degrees Celsius. Communications with Earth require power. Sensors, computers, medical equipment, manufacturing systems, all of it draws current every second of every day for years. The total power demand of a habitat large enough to call itself a second Earth would run into the megawatts. The obvious starting point is the sun. Solar panels have powered almost every spacecraft ever built, and for good reason. In the inner solar system, sunlight is abundant, free, and inexhaustible on any human timescale. The technology is mature, relatively lightweight, and requires no moving parts beyond the panels themselves. At Earth's orbital distance, a square meter of solar panel receives roughly 1,360 watts of sunlight. Solar intensity drops according to the inverse square of distance, which means that the farther you travel, the steeper the penalty. At Mars orbit, roughly 1.5 times Earth's distance from the Sun, solar panels produce only about 43% of what they would at Earth. You lose more than half your solar capacity just by traveling to the nearest planet worth visiting. Push out to Jupiter, 5 times Earth's distance, and the panels are producing roughly 3.7% of their Earth orbit output. For a second Earth spacecraft intended to operate across the solar system, solar power alone cannot be the answer. Nuclear fission is the next step up. Fission reactors have powered spacecraft before. Soviet satellites used them for decades, and the technology has continued to advance. NASA's Kilopower project and the associated K-Krusty reactor tests conducted at the Nevada National Security Site demonstrated a small fission reactor capable of producing up to 10 kilowatts of electrical power from a compact, uranium-fueled system. But the principle is proven, and scaling fission reactors upward is a well-understood engineering challenge. Small modular fission reactors, concepts being developed both for terrestrial use and for potential space applications, could realistically deliver hundreds of kilowatts or even a few megawatts from a unit compact enough to integrate into a large habitat. Fission does not care how far you are from the Sun. A reactor in Jupiter's shadow produces exactly as much power as it does at Earth orbit. It carries its own fuel, operates continuously, and can be shielded against its own radiation output with careful engineering. For a second Earth spacecraft moving through the outer solar system, a fission reactor provides something solar panels cannot: reliable baseline power regardless of position. There is also a third category, quieter and less glamorous than either of the others. Radioisotope thermoelectric generators, RTGs, have kept instruments alive on spacecraft for 50 years. The Voyager probes still return data today because of RTGs launched in 1977. They work by converting heat from the natural decay of radioactive material, usually plutonium-238, directly into electricity. But RTGs are low-power devices, and that constraint is fundamental rather than incidental. A typical RTG produces a few hundred watts, not kilowatts. They are ideal for keeping a probe's instruments running across decades of deep space travel. They are not a viable primary power source for a habitat that needs megawatts to keep its inhabitants alive. RTGs belong in the supporting cast of a second Earth's power system, not in the lead role, which brings the question to its most interesting answer. Fusion, the same process that powers the Sun, forcing light atomic nuclei together to release energy, has been pursued in laboratories on Earth since the 1950s, and for most of that time it remained perpetually 30 years away from practical use. That joke is aging. Commercial fusion companies, including Commonwealth Fusion Systems, TEI Technologies, and Helion Energy, have moved the timeline from theoretical to plausible within this decade. Commonwealth Fusion's spark reactor has already demonstrated record magnetic field strengths in its superconducting magnets, a key threshold for achieving ignition. Helion has a contract to deliver electricity to a grid customer by the end of this decade. The physics behind fusion has never been in doubt. The engineering challenges were always about containment, control, and efficiency, and those engineering challenges are finally beginning to yield. For a second Earth spacecraft, fusion offers something that no other power source comes close to matching. The fuel, isotopes of hydrogen, particularly deuterium and helium-3, is distributed throughout the solar system. Deuterium can be extracted from water, which the previous section of this script established is available in enormous quantities in asteroids and on the Moon. Helium-3 is present in the outer solar system in quantities that dwarf anything available on Earth. A fusion reactor running on deuterium consumes a remarkably small mass of fuel to produce a very large amount of energy. The power output relative to fuel mass is not comparable to any chemical or fission system, and the radiation output, while real, is manageable with shielding far lighter than what fission requires. A habitat powered by fusion would carry its fuel in tanks rather than shipping it continuously from a star 90 million miles away. The realistic power architecture for a second Earth spacecraft is probably layered. Solar panels for operations in the inner solar system, where they work well and add no mass penalty beyond the panels themselves. A fission reactor is a reliable baseline that keeps critical systems running regardless of solar distance or panel failure. And, eventually, a fusion reactor is the primary power source for the long voyages, the ones that take a habitat out past Jupiter into the deep solar system or beyond. The farther from the Sun you want to go, the more you need a power source that carries its fuel with it, And that has a name: fusion, even if it has not yet arrived in a form you can bolt to a spaceship. Chemical rockets work by setting things on fire, and the fundamental problem with this approach for moving a city through space is that fire is not nearly energetic enough. This is not an engineering failure, it is a chemistry ceiling. The most energetic chemical reactions humans have ever harnessed, liquid hydrogen burning with liquid oxygen, produce exhaust that leaves the nozzle at roughly 4 to 5 kilometers per second. That number is called specific impulse, and it is the currency of rocket efficiency. The higher it is, the less fuel you need to achieve a given change in velocity. For sending a capsule with 3 astronauts to the moon, chemical propulsion is adequate. For pushing a habitat the size of a small town to Mars and beyond, the math becomes catastrophic. There is an equation that governs all of this, and it has a name. Tsiolkovsky's rocket equation describes the relationship between a rocket's exhaust velocity, its starting mass, and the final velocity it can achieve. The brutal thing about this equation is that it is exponential. If your exhaust velocity is low, the fuel required to achieve a given velocity climbs at a ruinous rate. Double the destination distance, and you do not double the fuel requirement. You can easily multiply it by 10. A habitat carrying tens of thousands of tons of structure, water, soil, and people would require an absurd fraction of its own mass in propellant just to reach Mars on a reasonable schedule. The rocket equation punishes mass, and a second Earth spacecraft is nothing but mass. Nuclear thermal propulsion offers a meaningful step forward. Instead of burning fuel to produce heat, a nuclear thermal rocket uses a fission reactor to superheat a propellant, usually liquid hydrogen, and expel it through a nozzle. The exhaust velocity roughly doubles compared to chemical rockets, reaching around 8 to 9 kilometers per second. NASA developed and tested this concept extensively in the 1960s under a program called NERVA. The engines worked. The technology was real and demonstrated. For a crewed Mars mission with a modest payload, nuclear thermal propulsion would cut transit times significantly and reduce the fuel mass requirement dramatically compared to chemical systems. But even nuclear thermal is nowhere near sufficient for moving a genuine habitat. The exhaust velocity is still too low. The rocket equation still extracts its penalty. You are moving in the right direction, but nowhere near far enough. Fusion changes the arithmetic entirely. The exhaust velocity of a fusion-powered rocket would fall somewhere between 150 and 350 kilometers per second, depending on the specific design. That is not a modest improvement over chemical propulsion. That is a factor of 50 or more. When you feed those numbers into the rocket equation, the fuel fractions become manageable even for very large spacecraft. A habitat that would require an impossible quantity of chemical propellant to reach Mars could do it with a fusion engine carrying a fraction of the fuel mass. The physics favors it in every direction. The most promising specific concept currently under development is called direct fusion drive, and it comes out of the Princeton Plasma Physics Laboratory. The design is built around a configuration called a field-reversed configuration reactor, in which plasma is confined in a specific magnetic geometry that allows for stable fusion at relatively compact scales. What makes direct fusion drive unusual and genuinely remarkable is that it does not just produce thrust. The same reactor that accelerates propellant out the exhaust also generates electrical power for the spacecraft. One machine handles both jobs simultaneously. For a second Earth habitat, this is not a minor convenience. It means the power plant and the propulsion system are the same device. You eliminate an entire category of engineering complexity, reduce total mass, and simplify the systems that need to be maintained over a multi-decade voyage. The practical implications of fusion propulsion are worth holding clearly in mind. A conventional chemical mission to Mars, under favorable orbital conditions, takes roughly 8 months each way. That is 8 months of radiation exposure, 8 months of life support consumption, 8 months of psychological stress in a confined environment. A fusion-powered ship making the same journey could arrive in 90 days or fewer. That single change cascades through every other system on the vessel. The radiation shielding requirements drop. The food and water reserves needed for transit shrink. The psychological burden of the crossing decreases substantially. A faster ship is not just a faster ship, it is a less dangerous ship, a cheaper ship, and a psychologically more survivable ship. The honest accounting of where fusion propulsion stands today is that it remains theoretical as a propulsion technology. No fusion rocket has ever flown. No fusion reactor of any kind has yet produced more energy than it consumes in a sustained, operational sense, though that threshold has been crossed in brief laboratory demonstrations. The gap between a laboratory plasma that sustains fusion for a fraction of a second and a flight-rated engine is enormous. But here is the relevant context. The fusion reactions that a direct fusion drive would use, typically involving hydrogen isotopes like deuterium and helium-3, are the same reactions that dozens of commercial fusion companies are currently racing to achieve on Earth for power generation. Commonwealth Fusion Systems, TE Technologies, Helion Energy, and several others are operating at scales and timelines that would have seemed implausible 10 years ago. The fusion propulsion timeline almost certainly tracks the fusion power timeline by a few years. Once sustained fusion power is demonstrated on Earth, adapting the technology for propulsion is a serious engineering project rather than a speculative one. The scale point is worth stating plainly because it changes the way you think about the entire architecture of a second Earth spacecraft. Everything described in this script, the life support loop, the agricultural systems, the water recycling, the radiation management, the habitat structure, all of it requires continuous power. A fusion reactor providing that power is already running. It is already managing plasma at extreme temperatures. Directing some of that energy into accelerating propellant requires additional engineering, but it does not require a second reactor. The power plant becomes the engine. The engine becomes the power plant. That is the elegance that separates fusion from every other propulsion concept seriously under consideration. A single fusion engine powering a habitat the size of a small town while also pushing it toward the outer solar system is not a fantasy. It is an engineering specification waiting for the right reactor, and the reactors are getting closer every year. The human brain spent roughly 2 million years being shaped by a planet full of open horizons, seasonal change, social groups of a specific size, and the ability to walk away from a conflict that was going nowhere. Every engineering system covered so far has a solution that is, at minimum, theoretically achievable. Gravity is a matter of rotation. Radiation is a matter of shielding. Food is a matter of hydroponics and light. But the mind is not a mechanical system, and it does not respond to engineering fixes the way a life support loop does. This is the part of the problem that gets the least attention in the technical literature, and it may be the hardest part of all. In 2010, a group of 6 healthy men entered a sealed facility in Moscow and did not come out for 520 days. The project was called MARS 500. The facility was designed to simulate, as faithfully as possible, a crewed mission to Mars and back. The participants were medically screened, psychologically evaluated, and carefully selected. What happened to them anyway is worth understanding in detail. By the later stages of the simulation, most of the crew had developed significant sleep disruption. Physical activity dropped sharply. Several participants began sleeping up to 11 hours a day while becoming increasingly sedentary during waking hours. The researchers observed a pattern they described as psychological distancing, a gradual withdrawal from social engagement, a flattening of emotional response, a retreat inward. Nobody had a breakdown. Nobody had to be removed. The mission, technically, succeeded, but the human beings inside it were not the same people who had entered, and the changes were not improvements. MARS 500 lasted 520 days. A real Mars mission, depending on the orbital mechanics, could last somewhere between 500 and 900 days. An O'Neill cylinder carrying a permanent population would last indefinitely. The psychological pressures do not diminish with time. The research suggests they compound. The International Space Station offers a shorter but real-world data set. Astronauts on 6-month rotations have documented behavioral health challenges with enough frequency that NASA established an entire program around them. Crews have reported interpersonal friction with other crew members. Mission controllers on the ground have reported friction with crews. There are documented cases of astronauts reducing their communication with mission control as missions progressed, a phenomenon researchers refer to as psychological closing off. These are people who trained for years, who were selected partly for psychological resilience, and who knew exactly what they were getting into. 6 months in a confined environment still change their behavior in measurable ways. Now consider the communication delay problem. On the ISS, if a crew member is struggling, a psychologist on the ground can respond in seconds. At Mars distance, a one-way signal takes between 3 and 22 minutes depending on orbital position. A conversation becomes an exchange of letters. Real-time emotional support becomes impossible. The crew is, in the most practical sense, alone in a way that no crew in ISS history has ever been. This matters enormously because one of the most effective interventions for psychological distress in confined environments is simply being heard by someone outside the situation. Remove that option, and the internal dynamics of the crew become the only resource available. The deeper issue is sensory. Humans did not evolve for metal corridors. The brain expects variety, the angle of light changing through the day, the temperature shifting with the seasons, the smell of rain on dry ground, the sound of wind in vegetation, the visual complexity of a landscape that was not manufactured. None of those things exist in a spacecraft by default. What exists instead is a set of surfaces that look exactly the same today as they did yesterday, and will look exactly the same a year from now. The monotony is not just aesthetic, it is neurological. Research on sensory-restricted environments consistently shows that the brain begins to generate its own stimulation when external variety falls below a threshold, and that process is not pleasant. The countermeasures the research supports are worth naming clearly. Access to natural spectrum lighting that cycles through a genuine day and night rhythm matters significantly. The ability to look at natural imagery, whether through an actual window or a high-quality display showing Earth, the stars, or recorded natural environments, shows measurable benefit in stress reduction. Private space is non-negotiable. Every individual needs somewhere they can be completely alone, and the ISS experience consistently shows that the absence of genuine privacy accelerates psychological deterioration faster than almost any other single variable. Exercise is well established as a stabilizer for both mood and cognition, which is why it is already mandatory on the ISS. Meaningful work with genuine autonomy, the sense that what you are doing matters and that you have some real control over how you do it, turns out to be one of the most powerful protective factors known. Social structure deserves its own consideration. Conflict is not avoidable in confined spaces. It is guaranteed. What determines whether conflict destroys a group or gets managed is partly personality and partly the structure of the environment. In a normal terrestrial conflict, there is a simple resolution available that does not require anyone to win. You can leave. In a sealed spacecraft, nobody can leave. This changes the stakes of every disagreement in ways that are difficult to fully appreciate from the outside. Small frictions that would dissipate naturally in an open environment instead accumulate. The research on Antarctic overwinter stations, submarine crews, and polar expeditions all converges on the same finding. How a group handles conflict in the first few months of confinement predicts almost everything about how it will function a year later. This has design implications that are not usually framed as engineering problems, but should be. Windows are not a luxury item to be cut in a mass optimization review. They are a psychological intervention. Green spaces filled with growing plants are not decorative. They provide sensory variety, biological connection, a quality of light and smell that no display can fully replicate, and evidence that the closed-loop system around you is actually working. The design of a second Earth spacecraft is not separable from the design of a livable psychological environment. The two problems are the same problem. You can solve every engineering problem in this script, gravity, radiation, food, water, power, and still lose the mission to something that does not show up in any structural diagram, which is what happens to people when they have been sealed inside a metal container for long enough. The most expensive square meter in a space habitat is the one that serves no obvious engineering function, but exists purely to give someone a reason to feel calm. That sounds like a luxury. It is not. The previous section laid out what prolonged confinement does to the human brain: the sleep disruption, the psychological withdrawal, the slow erosion of motivation that no amount of mission discipline can fully prevent. If those effects are real, and the research confirms they are, then designing against them is not optional. It is engineering. The question is what that design actually looks like when you are building something that has to work for decades. The concept researchers keep returning to is biophilic design. The word comes from the idea that humans have a deep, evolved affinity for living systems: plants, water, natural light, the sound of moving air. Strip those elements away entirely, and something in the brain registers the absence. Not immediately, not dramatically, but steadily, across months and years, the deprivation compounds. Biophilic design says you build those elements back in deliberately. Running water features in common areas, living plant walls in corridors, lighting systems that shift color, temperature, and intensity through a full day-night cycle, warmer and dimmer at the ends of the cycle, bright and blue-white in the middle, views of space through large windows because open sky, even infinite dark sky, satisfies something that a painted wall does not. None of this is guesswork. Antarctic overwinter stations have been running these experiments for decades because a research team locked into a base at the South Pole through 6 months of polar darkness is a reasonable first approximation of a deep space crew. The data from those stations is consistent. Crews with access to full spectrum lighting that mimics daylight show lower rates of depression and better sleep patterns than crews in flat fluorescent environments. Crews with common dining areas and shared meal rituals maintain group cohesion longer than those who eat whenever and wherever they choose. Small things accumulate into large outcomes across a long enough timeline. Here is where the agricultural sections of this script connect to the psychological ones. The hydroponic farms and growing chambers described earlier are not just food systems, they are the greenest, most biologically alive spaces in the entire habitat, and that matters. A crew member who spends 30 minutes tending plants is not just performing a life support function. The research on therapeutic horticulture is extensive enough that several long-duration mission planners have started treating agricultural time as a psychological countermeasure rather than just labor. The farm is green. It smells of soil medium and growing things. It has different humidity and temperature than the rest of the ship. That sensory contrast is itself a form of relief. Private space is non-negotiable. This point sounds obvious and gets underweighted in almost every small habitat design because private space is volume and volume is mass and mass is money. But the psychological data on confinement is unambiguous. Every person needs a place they can close a door and be completely alone, with no obligation to perform, no awareness of being observed, no requirement to be collegial. Crews that have this show lower interpersonal conflict rates. Crews that lack it develop friction that compounds until it becomes a mission risk. The design implication is uncomfortable but clear. You cannot pack people in like a submarine crew and expect them to thrive over years. The berth has to be big enough to sit up in, lie down in, and feel like a room rather than a drawer. Communal architecture matters in the opposite direction. Private space protects the individual. Shared space builds the group. Antarctic research suggests the specific design of communal areas influences behavior. Large open spaces encourage informal gathering, which is different from the more structured interaction of a scheduled meeting or a shared task. A habitat that wants cohesion needs places where people can end up together by accident, not just by schedule. A common area with comfortable furniture, a table large enough for the whole community, and enough ambient warmth to make it feel chosen rather than mandatory. Autonomy is perhaps the least tangible factor and possibly the most powerful. Studies consistently show that crews who have meaningful control over their schedules, their work priorities, and their daily environment cope far better with confinement than those who are highly managed from outside. This has a direct implication for the relationship between a deep space habitat and any mission control on Earth. At interplanetary distances, the communication delay alone makes real-time direction impractical. A crew 6 light minutes from Earth receives advice that is already 12 minutes old by the time they can reply. The system has to be designed for crew autonomy, not just as a psychological preference, but as a functional necessity. And the research says this is not a trade-off against safety, it is a condition for it. Automated mental health support is an emerging area that deserves attention. Several research groups are developing AI-based psychotherapy systems capable of providing confidential, real-time support to individuals when human therapists are not available. These are not chatbots offering encouragement. The more advanced versions are trained on therapeutic protocols and capable of recognizing early warning signs in language patterns and behavior. For a crew operating years from Earth, these systems are not a supplement to professional mental health support. They are the primary layer of it. NASA's Behavioral Health and Performance Group has been building toward this architecture for years, drawing on ISS experience and simulation data. Then there is the population question. Psychological health in enclosed communities improves significantly above a certain community size. Below roughly 150 people, social variety runs thin. The same individuals fill every social role, every relationship, every possible conflict and resolution. Research on small community dynamics, Antarctic stations, remote research posts, isolated villages, suggest that somewhere between 150 and 300 people, something shifts. There is enough social variation to support healthy group dynamics, enough diversity of personality and interest to prevent the kind of social exhaustion that comes from knowing everyone's every mood in advance. This is not a small design implication. It means a psychologically viable second Earth spacecraft is not a large cruise ship. It is a small town. A second Earth is not just a spacecraft that keeps its passengers alive. It is a place where someone could be born, grow up, fall in love, and die without ever setting foot on a planet. And that is a fundamentally different design problem than any spacecraft that has ever been built. Every system described in this script has a minimum scale below which it stops working. And the uncomfortable truth is that when you add all those minimums together, the resulting spacecraft is the size of a town. Start with food. A hydroponic system running at high efficiency needs somewhere between 20 and 40 square meters of growing area to feed one person. For a crew of 100, you are looking at 2,000 to 4,000 square meters of agricultural floor space under continuous artificial light, drawing continuous power, maintained by people who understand plant biology, nutrient chemistry, and the failure modes of sealed growing systems. Scale that to 1,000 people, and the farm alone occupies several hectares. This is before you have built a single bedroom, a single corridor, or a single water processing unit. Water adds another layer. The recycling systems discussed earlier can recover close to 95% of what the crew uses, but that remaining 5% has to come from somewhere, and the total volume of water in active circulation, drinking, hygiene, agricultural irrigation, radiation shielding panels, is substantial. The ISS carries water reserves and receives resupply. A truly closed habitat cannot do either. It needs enough stored volume to absorb failures in the recovery loop without running dry, and it needs the mechanical redundancy to keep recovering water even when components break. That means multiple independent systems, spare parts for each one, and the trained operators to fix them when something goes wrong at 3 in the morning, 400 million miles from the nearest hardware store. Living space is a number that sounds generous until you do the math at scale. The ISS provides roughly 90 cubic meters per crew member. That works for 6 people on 6-month tours. It would not work for 500 people trying to live normal lives over decades. Comfortable long-term habitation, the kind where people do not lose their minds, probably requires several times that volume per person, including private quarters, communal areas, green space, and somewhere to go when you need to be alone. The architectural research from Antarctic stations and submarine deployments points in the same direction. Below a certain density, people become irritable and unstable. Crowding is not just uncomfortable, it is a mission risk. Here is something the numbers do not fully capture. Small closed ecosystems are fragile. The Melissa project in Barcelona can cycle nutrients through a controlled biological loop at laboratory scale and keep a community of rats alive indefinitely. That is a remarkable achievement, but a habitat supporting thousands of humans needs ecological resilience that a laboratory loop cannot provide. Resilience requires redundancy. Redundancy requires diversity. Biodiversity, in the microbial communities cycling nutrients, in the plant species producing oxygen and food, in the fungal network supporting root systems, is not an aesthetic choice. It is the engineering specification for a system that has to keep running when one component fails. A monoculture farm in a sealed environment is one fungal outbreak away from catastrophe. You need more species, more variety, more buffer capacity, and all of that requires more space. Then there is the manufacturing problem. A ship that leaves Earth for a multi-decade voyage will break things. Seals wear out, pumps fail, circuit boards develop faults. On the ISS, broken components are either repaired with spares launched from Earth or worked around until the next resupply. Neither option exists on a truly self-sufficient spacecraft. It must carry the manufacturing capacity to produce its own replacement parts, which means machine tools, raw material stocks, people who know how to use them, and enough physical space to run a small industrial operation. And the people who operate it need to be trained, which means they need time to train, which means the habitat needs to carry people who are not directly engaged in food production or life support at any given moment. People who are learning, researching, teaching, building institutional knowledge for the next generation. Which brings the question to genetics. A habitat that carries people on a multi-generational voyage faces a problem that has nothing to do with engineering. It has to do with population biology. A founding population that is too small will accumulate genetic problems over generations through inbreeding depression. The minimum viable founding population for a multi-generational voyage, according to population genetics research, sits at roughly 160 to 200 people if the genetics are carefully managed. A more realistic target, one that allows for natural social structures, genetic diversity, and the inevitable reality that some people will not reproduce, is over 1,000. Pull all of this together: agricultural space for thousands of people, water systems with full redundancy, living volume that does not drive inhabitants to psychological collapse, an ecological support system diverse enough to absorb failures. a manufacturing capability that can keep the hardware running indefinitely, a population large enough to maintain genetic health across generations and carry the institutional knowledge to operate every system without help from Earth. The structure that fits all of those requirements is not a spacecraft in any sense the word currently implies. It is not the size of the ISS. It is not the size of a naval vessel. It is closer in scale to an O'Neill cylinder, something miles long, miles wide, housing millions of cubic meters of pressurized volume. No government has funded that. No company has proposed a credible construction timeline for it. The largest space structures ever built are toys by comparison. And yet, every component is in active development. The agricultural systems are running. The life support loops are being tested. The population genetics models have been published. The engineering specifications exist. What does not exist is the coordination, the funding, and the decision to treat this as a serious near-term goal rather than a distant aspiration. That decision has not been made, but the preconditions for making it are assembling in ways they were not 20 years ago. The number that keeps coming back from every independent analysis: genetic diversity, ecological closure, manufacturing self-sufficiency, psychological resilience, is somewhere between 1,000 and 10,000 people, which is not a spacecraft by any current definition. It is a civilization. None of the systems described in this script require the discovery of new physics. They are all applications of principles that are already understood. The research programs developing them are already running. The question then is not whether the science permits this. It is what gets built first and in what order, and who decides to pay for it. The most immediate stepping stone is already in progress. NASA's Artemis program is putting humans back near the moon. Embedded in that architecture is something more consequential than the landings themselves. The Lunar Gateway, a small space station orbiting the moon, is designed to operate with reduced resupply from Earth. Not zero resupply, not full closure, but reduced deliberately as a test. For the first time since Apollo, humans will be sustaining themselves at a distance where a resupply ship takes days, not hours, to arrive. That constraint forces the kind of engineering discipline a second Earth spacecraft will ultimately demand. Every kilogram of water recovered, every breath of oxygen regenerated, every calorie grown in orbit rather than launched from a factory in Florida, all of it matters at the Gateway in a way it simply did not on the International Space Station, where a cargo vehicle could dock in 2 days if something went wrong. The moon itself is where the most critical near-term work will happen. Not the Gateway above it, but the surface. Permanently shadowed craters near the lunar south pole hold water ice confirmed by multiple missions, billions of tons of it, sitting in the dark at temperatures close to absolute zero. Extracting that water, processing it, using it to sustain a crew and potentially splitting it into hydrogen and oxygen for propellant, that is the first real test of in situ resource utilization at human scale. If it works on the moon, the same logic transfers to asteroids and eventually to locations far deeper in the solar system. The moon is a laboratory 25 seconds of light travel away. Every mistake made there is recoverable. Every lesson learned there is irreplaceable. Then there is the commercial dimension, and it is moving faster than most government programs. Axiom Space is constructing the first commercial modules to attach to the ISS, with the long-term plan of detaching them into a freestanding private station. Orbital Reef, led by Blue Origin and Sierra Space, is a different commercial station concept intended to be operational before the end of this decade. These are not second Earth spacecraft. They are not designed to be self-sustaining, but they are the platforms on which self-sustaining systems will first be tested at operational scale, with paying customers and genuine engineering accountability rather than government-funded research protocols. The transition from experiment to product has historically been the phase that accelerates everything. SpaceX's Starship changes the economic foundation of this entire conversation. Every large structure described in this script, an O'Neill cylinder, a Stanford torus, anything remotely resembling a second Earth spacecraft, requires an enormous mass to be placed in orbit or assembled in space. With current rockets, that mass costs somewhere between $1,000 and $10,000 per kilogram just to reach low orbit. Starship, in its intended operational state, is designed to bring that number down by an order of magnitude or more. That is not a marginal improvement, it is a phase transition. The engineering of a second Earth does not change, but the economics of beginning to build it does, fundamentally and permanently. The research priorities are reasonably clear. ESA's Melissa project has been running its closed-loop biological system for decades and has a functioning pilot facility in Barcelona keeping organisms alive in a sealed ecosystem. What it has never done is demonstrate full biological closure at human scale. That demonstration needs to happen. It needs a crew-sized habitat, not a laboratory bench. It needs to run for years, not months, with real biological noise and real failure modes and real repairs. Until that exists, the life support loop for a second Earth spacecraft is a concept rather than a proven system. Radiation shielding is in a similar position. The physics of active magnetic deflection is solid, superconducting magnet technology is advancing. But no one has ever deployed an artificial magnetosphere around a crewed vessel in actual deep space. That test needs to happen. The Lunar Gateway, or an early Mars transit architecture, is the logical place to run it. The wild card in the timeline is fusion. If a working fusion reactor reaches operational status in the next 15 to 20 years, and several well-funded private companies are explicitly racing toward that target, the power and propulsion problem for a second Earth spacecraft changes overnight. Fusion does not just improve the situation, it unlocks capabilities that are simply unavailable without it. Sustained high-thrust propulsion across the outer solar system, abundant power for life support and food production in deep space where solar panels produce almost nothing. Eventually, the possibility of journeys measured in weeks rather than years. The fusion timeline is uncertain enough that no serious planner should depend on it, but optimistic enough that no serious planner should ignore it. No single nation will build this alone. The ISS was assembled despite deep political friction between its partners, including periods of genuine geopolitical hostility between the United States and Russia. The hardware still docked, the crews still worked, the science still ran. That history matters, because the political will required to build something at civilizational scale has to survive election cycles, budget crises, the inevitable disasters that any program of this ambition will eventually encounter. International cooperation is not just an idealistic preference, it is a structural necessity. This was because the cost and complexity of this project exceed what any single program, government, or company can absorb. The gap between what humanity can do right now and what would be required to build a genuine second Earth is not a gap in physics. It is a gap in money, coordination. The decision to treat this as urgent, and gaps like that have closed before. The practical case for building a self-sustaining spacecraft is relatively easy to make, but the real reason this project matters is not practical. It is the oldest reason human beings have ever done anything dangerous and expensive. The planet we live on has been struck before. The asteroid record is not a curiosity. It is a log of near extinctions and actual ones, written in craters and in the fossil record and in the abrupt disappearance of entire branches of life. 66 million years ago, an object roughly 10 kilometers wide ended the reign of every large animal on Earth in a matter of weeks. That was not the first time, and, statistically, it will not be the last. The question is not whether a catastrophic strike will happen again. The question is whether anyone will be somewhere else when it does. The asteroid risk is only the beginning of the list. In 1859, a solar storm known as the Carrington event induced electrical currents strong enough to shock telegraph operators and set paper on fire. A storm of equivalent scale striking today would collapse power grids across entire continents, disable satellite infrastructure, and knock out the communication systems that modern civilization runs on. The recovery time, by most serious estimates, would be measured in years. A civilization that depends entirely on electrical infrastructure distributed across one planet has a single point of failure. That is not a theoretical concern. It is a known vulnerability with a documented historical precedent. Further out on the timeline, the risks become even less avoidable. A sufficiently close supernova could strip Earth's ozone layer. A gamma ray burst from the right direction could sterilize one hemisphere in seconds. These events are rare on human timescales, but not on astronomical ones. And on the longest timescale of all, the Sun itself will expand into a red giant and make the inner solar system uninhabitable. That is roughly 5 billion years away, which sounds like enough time. But a civilization that waits until the deadline to solve a problem it could solve now is not a civilization that plans well. The statistical argument is simple and hard to argue with. Any civilization confined to one world is one catastrophe away from ending. Given enough time, catastrophes become mathematically certain. The only way to change that probability is to exist in more than one place. But that is the survival argument, and the survival argument, while true, misses something. A second Earth is not just an insurance policy. What gets carried aboard it is not just a genetic library and a food supply. It is language. It is music. It is the accumulated knowledge of every human generation going back to the first people who looked up and tried to understand what they were looking at. Carrying that into space is not the same thing as storing a backup file. It is an act of deliberate continuation, a decision that what humans have built and felt and thought and made is worth preserving at extraordinary cost. That framing has its complications. The people who would actually live aboard a second Earth spacecraft, who would grow up inside it, raise children in it and eventually die in it, would not experience it as an ark or a backup. They would experience it as home. The cultures that develop inside a generation ship would diverge from Earth's cultures the way any isolated community diverges from its origin. New traditions would form, new languages would develop, or old ones would shift in ways the origin world would barely recognize. The relationship to Earth would become increasingly abstract over generations. The way the relationship between a modern American city and medieval Europe is now abstract, a matter of ancestry rather than lived experience. This is not a failure of the project. It is the inevitable result of it. A second Earth does not preserve humanity. It continues humanity in a new context with new pressures, producing something genuinely new. Preservation and transformation are not opposites here. They are the same process seen from different angles. You preserve the line by allowing it to change. What makes this moment significant is that none of what has been described across this script is waiting on a scientific breakthrough. The fundamental physics is settled. The engineering challenges are real, but they are engineering challenges. Problems of manufacturing, materials, scale and cost, not problems of principle. Hydroponics works. Centrifugal gravity works. Closed-loop water recovery works. Magnetic shielding is understood well enough to be designed. Fusion is getting closer every year. The individual systems are either already demonstrated or clearly within reach. What is missing is the decision to assemble them. Somewhere on Earth right now, someone is running a closed biological loop in a test chamber in Barcelona. Someone else is modeling superconducting magnet arrays for spacecraft radiation shielding. Someone is calculating the crop yield of a hydroponic wheat system under LED lighting. All of them are working on different pieces of the same object. The technology is in the labs. The physics is in the textbooks. The blueprints are in the archives. And somewhere out in the solar system, the materials for building it are drifting in silent orbits, waiting for someone to go and get them.